In this video, we'll explore C++ pointers. Pointers are variables that store memory addresses. They provide direct access to memory locations and are essential for dynamic memory allocation, data structures, and efficient parameter passing. In the memory illustration, the first memory cell shows the address 0x7ffd5, storing the value 42. The second memory cell shows the address 0x7ffd9, storing the value 0x7ffd5. The third memory cell shows the address 0x7ffdd, storing the value hello. This slide explains pointer declaration and initialization in C++. The code snippet shows how to declare and initialize pointers. First, an integer variable number is initialized with the value 42. Then, an integer pointer PTR is declared and initialized to store the memory address of number using the ampersand operator. This means PTR now points to number. Next, the value of number is accessed through the pointer PTR using the asterisk operator and assigned to the integer variable value. Finally, the value of number is modified through the pointer PTR by assigning it the value 100. This changes the original value of number to 100. Key points to remember are: the asterisk symbol declares a pointer variable. The ampersand operator returns the memory address of a variable. The asterisk operator, also known as dereference operator, accesses the value at an address. Changes made through a pointer affect the original variable. This slide visualizes how pointers work in memory. The code snippet declares an integer variable number and initializes it to the value 42. Then, it declares an integer pointer PTR and assigns it the address of number using the ampersand operator. This means PTR stores the memory address of number. The comments highlight that PTR stores the address of number and asterisk PTR accesses the value at that address, which is 42. The memory diagram shows two memory cells. The first cell has the address 0x7ffd5, stores the value 42, and is labeled as number. The second cell has the address 0x7ffd9, stores the value 0x7ffd5, and is labeled as PTR. A dashed arrow originates from the PTR cell and points to the number cell, illustrating that PTR holds the memory address of number. This slide explains common pointer operations in C++. The code initializes an integer array ARR with 5 elements: 10, 20, 30, 40, and 50. Then, an integer pointer P is declared and initialized to point to the first element of the array, ARR. The comments indicate that P points to ARR at index 0. Pointer arithmetic. The code demonstrates pointer arithmetic. Int second equals asterisk open parenthesis P plus 1 close parenthesis retrieves the value of the second element of the array, which is 20. Int third equals P square bracket 2 is equivalent to retrieving the value of the third element of the array, which is 30. Incrementing pointers. The code increments the pointer P. This advances the pointer to point to the next element in the array, which is ARR at index 1. Then, int val equals asterisk P assigns the value pointed to by P to the integer variable val, making val equal to 20. The operations include: P plus n advances the pointer by n elements, not bytes. P minus n moves the pointer backward by n elements. P plus plus increments the pointer to the next element. P minus minus decrements the pointer to the previous element. P square bracket I is equivalent to asterisk open parenthesis P plus I close parenthesis, which is array notation. This slide discusses null pointers and safety in C++. The code shows two ways to declare a null pointer. The first uses the nullptr keyword, which is the preferred modern C++ approach. The second uses null, which is a traditional C-style null pointer, requiring the inclusion of the cstdlib header. The code then demonstrates how to check for a null pointer before dereferencing it. It uses an if statement to ensure that ptr1 is not equal to nulpter before attempting to access its value. This prevents undefined behavior and potential program crashes. A null pointer is a pointer that doesn't point to any valid memory location, indicating that a pointer doesn't currently have a valid target. Dereferencing a null pointer causes undefined behavior, typically resulting in program crashes. Best practices are to always initialize pointers, check pointers before dereferencing, and use nulpter in modern C++ versions from C++11 and later. This slide explains the relationship between pointers and arrays in C++. The code initializes an integer array ARR with 5 elements: 10, 20, 30, 40, and 50. It then declares an integer pointer ptr and assigns it the value of ARR. In C++, the name of an array decays to a pointer to its first element. Accessing array elements is shown using 3 methods. Int val1 equals ARR square bracket 2 accesses the third element of the array using array notation. Int val2 equals asterisk open parenthesis ptr plus 2 close parenthesis accesses the third element by adding 2 to the pointer ptr, and then dereferencing it. Int val3 equals ptr square bracket 2 accesses the third element using pointer arithmetic, which is equivalent to array notation. All 3 methods result in val1, val2, and val3 being assigned the value 30. The array visualization shows the array ARR, with its elements and their respective addresses. The pointer visualization shows the pointer ptr, holding the address 0x100, which is the address of the first element of the array. A note says that in C++, array names decay to pointers to their first elements. This slide covers dynamic memory allocation in C++. Single object allocation. First, memory is allocated for an integer using the new keyword, and the pointer ptr stores the address of the allocated memory. Then, the allocated memory is initialized by assigning the value 42 to the memory location pointed to by ptr. The allocated memory is used by assigning the value at ptr to the integer variable value. Finally, the allocated memory is freed using the delete keyword, and ptr is set to nulpter to prevent dangling pointers. Array allocation. The code allocates memory for an array of 5 integers using new int square bracket 5, and the pointer ARR stores the address of the first element of the allocated array. Next, the array elements are initialized using a for loop. Finally, the allocated array memory is freed using delete square bracket ARR, and ARR is set to nulpter. The dynamic memory lifecycle illustrates how the new operator requests memory from the heap. Memory is allocated and a pointer to it is returned. The memory is used through the pointer, and the delete operator releases the memory back to the heap. Failing to delete allocated memory causes memory leaks. This slide is about function pointers. The code defines 2 functions: add, which takes 2 integer arguments and returns their sum, and subtract, which takes 2 integer arguments and returns their difference. A function pointer operation is declared. This pointer can point to functions that take 2 integer arguments and return an integer. The address of the add function is assigned to the operation pointer using operation equals ampersand add. The add function is called through the pointer using operation open parenthesis 5, 3 close parenthesis, and the result is stored in the variable result, making result equal to 8. The function pointer is changed to point to the subtract function using operation equals subtract. The subtract function is called through the pointer, and the result is stored in result, making result equal to 2. Function pointers are variables that store the addresses of functions, allowing functions to be passed as arguments, returned from other functions, and called dynamically. Common use cases are callback functions, plugin architectures, strategy pattern implementation, and event handling systems. In modern C++, consider using std::: function from the functional header for a more flexible and type-safe approach to function pointers. This slide discusses common pitfalls when working with pointers in C++. The first pitfall is dereferencing null pointers. Attempting to access the value at a null pointer causes undefined behavior, typically resulting in program crashes. For example, if int pointer ptr equals nullptr, then trying to access the value at ptr with int value equals *ptr will cause a crash. The solution is to always check if a pointer is null before dereferencing it. The second pitfall is memory leaks. Failing to free dynamically allocated memory leads to memory leaks, which can exhaust system resources. For example, if int pointer ptr equals new int square bracket 100, and the memory is not freed with delete square bracket ptr, it will result in a memory leak. The solution is to always match new with delete, and new square bracket with delete square bracket. Consider using smart pointers. The third pitfall is dangling pointers. Pointers that reference memory that has been freed or is no longer valid can cause unpredictable behavior. For example, if int pointer ptr equals new int open parenthesis 42 close parenthesis, and the memory is deleted with delete ptr, then ptr becomes a dangling pointer. Accessing the value at ptr with int value equals *ptr will lead to undefined behavior. The solution is to set pointers to nullptr after deletion. The fourth pitfall is buffer overflows. Accessing memory beyond the bounds of an allocated array can corrupt memory and cause security vulnerabilities. For example, if int pointer arr equals new int square bracket 5, and you try to access arr square bracket 10 equals 42, it will cause a buffer overflow. The solution is to always check array bounds before access, and consider using std::vector or std::array. This slide provides best practices for working with pointers and modern alternatives in C++. Always initialize pointers to nullptr if they don't point to valid memory immediately. Validate that pointers are not null before dereferencing them. Always delete dynamically allocated memory when it's no longer needed. Prefer smart pointers over raw pointers for automatic memory management. Modern C++ alternatives. std::unique pointer is an exclusive ownership smart pointer that automatically deletes the object when it goes out of scope. std::shared pointer is a shared ownership smart pointer that keeps track of how many references exist and deletes the object when the count reaches 0. std::vector and std::array are container classes that manage memory automatically and provide bounds checking. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.